In this chapter, we'll take a high-level overview into HDFS architecture. We'll explore the core concepts and the daemons involved, as well as how HDFS does heartbeating, block reporting, and checksums. Again, HDFS is a distributed file system. This means that it has master and slave daemons. If we take out all the green daemons, we're left with these three daemons: a name node and a secondary name node, one each on a master machine, and data nodes running on each of the slaves. It should be noted that HDFS can run completely independent of MapReduce. If we just wanted a distributed, highly redundant, relatively good performant file system, we could use HDFS just by spinning up these daemons. Again, HDFS is just the combination of these daemons. When we load data, say a file, into HDFS, we split that data up into chunks, or what's known in HDFS as blocks, and we distribute those blocks on the slaves. Each block is replicated or copied a default number of 3 times for durability and concurrent access. HDFS is what's known as a write-once, read-many file system, which has the ungratifying acronym of WORM. This means that we can't do any appends or edits. Once we write a file into HDFS, even if we wanted to just go in and flip a bit in the middle of the file, we have to delete the whole file and rewrite the entire file. The read-many part of the WORM acronym has to do with the fact that because each block is replicated now 3 times, we can do 3 times the concurrent access because we now have at least 3 disk heads working on our behalf. HDFS is completely self-healing. It can survive the loss of an entire slave node or individual blocks of a single file. Looking again at some more core concepts, HDFS is again a distributed file system. The clients will cut files into the same size blocks at load time. This is what's known as the block size. By default in Hadoop, that's set to 64 megabytes, but we recommend changing it to 128 megabytes. Like almost everything in Hadoop, the user has complete control over this, and some users may even want to go higher than that 128 megabyte block size. Files also have what's known as a replication factor, or RF. This is the number of times that a block will be replicated inside of HDFS. Each block is then loaded on exactly RF number of nodes. So if our replication factor is set to 3, that block will persist on 3 independent data nodes, each with their own hardware. The block loads happen randomly at load time. Zooming in on the HDFS daemons, we see our old friend the name node, which is our master node that clients have to initiate a read or write operation to. It contains all the metadata information about a file. This includes the file name, the associated permissions, and the directory that that file exists in. It also contains which blocks are loaded into which nodes, so that when asked, the name node can reconstruct a file. This metadata is stored both in memory for quick lookups and on disk for persistence. The name node is a very memory-hungry daemon. Making sure we have plenty of backups of the name node metadata is very, very important. If you lose the name node, you essentially lose HDFS. I like to give the analogy of the blocks being independent puzzle pieces stored on each individual data node, and the name node being the picture of the puzzle that's on the cover of the box. Without the cover of the box, all we have is a bunch of independent pieces. Although each data node maintains information about its individual blocks, it doesn't know which blocks belong to which file. That is the name node's purpose. If you lose name node, again, you lose HDFS. There's no block data ever flowing through the name node. The actual raw blocks of the data files that we store go directly into the data node, as explained in another chapter. The data node daemons, again, are slave nodes that perform the actual block storage. When requested, the client does direct write to and read from the slaves. File data never ever flows through the name node. Let's talk a little bit about how name node persists that metadata to disk. It persists it really in 2 files. One is called an FS image, which is a point-in-time snapshot of what HDFS looks like, and also an edits log, which is all the deltas or changes to HDFS since that snapshot. The FS image and the edits log are periodically merged back into a single FS image. This happens either every time the name node is restarted or by the secondary name node, which is covered in the secondary name node lesson. By using this smaller edits log, we're able to open a much smaller file and write our deltas to a smaller file. If we didn't use the edits log, we would constantly be opening and closing a very large file in the form of the FS image, and HDFS's performance would suffer. The writes of these files, both the FS image and the edits log, are done synchronously to all attached name node storage directories. I highly recommend using at least 2 local, perhaps mirrored rated disks on the name node, as well as remote NFS mount point and heavy monitoring of all these disks. It's also highly recommended to do offsite daily or weekly full FS image backups. Again, if you have one purpose in life as a Hadoop administrator, it's to make sure we never ever lose the FS image and the edits log. Let's talk a little bit about heartbeats. Both the processing and the HDFS daemons use heartbeats. In the case of HDFS, our data nodes heartbeat every 3 seconds into the name node. Again, this is changeable. This heartbeat is saying, hey, name node, I'm alive, I'm part of the cluster, I'm here. I can accept block read and write requests. So if somebody requests a block that I have, please connect me. Or if you need somewhere to store data, please use me. If a data node doesn't report 10 heartbeats consecutively, the name node takes it out of rotation for reads and writes. If after that 30-second period, a data node doesn't send any more heartbeats in 10 minutes, any blocks that it was storing are re-replicated. This means that the name node is constantly aware of and updating that replication factor to ensure that if any data node software or hardware goes offline, that replication factor will be maintained. The data nodes also send what are known as block reports every hour into the name node. These block reports say, hey name node, here's the blocks that I have. If the name node again sees fewer or more blocks than the replication factor, it asks another data node in the cluster to pull that block across the network from a data node that has it. This is obviously in order to maintain that replication factor. Block reports are also sent on initial registration of a data node with the name node. This means that when we restart the name node, the data nodes will automatically send a block report, so the name node doesn't have to wait that 1-hour period before it has a picture of the file system. HDFS also uses checksums to ensure the integrity of the data that's written. A write time checksum is generated every time a block is written into the data node. This is written as a file directly next to the block on the hard disk of the data node. Every time a client makes a subsequent read of that block from the data node, the read time checksum is compared to the write time checksum, and if a block is corrupt, the client is directed to another data node. The name node is notified that this data node no longer has a valid block and it's under-replicated, and then the name node handles the re-replication of the block, just as we saw in the previous slide. The data node also runs an independent checksum validation every 3 weeks. So even if a client doesn't read a block within 3 weeks, the bad blocks are detected and handled the same way that we saw in the previous slide. In this deck, we did an HDFS overview, looked at the core concepts, the daemons, and investigated the heartbeats, block reports, and checksums. In conjunction with this deck, it's also highly recommended you review the HDFS file write walkthrough deck.